to reduce accumulative errors, even they are small, in short simulations. Next page. Next slide. To give you example here. So here I show a figure of the evolution of simulated global mean sea surface height of 100 years using an old version of E3SM. So this is the Alpha 6 version. This simulation is the 1850 control simulation, meaning that the external forcing is fixed. So we are not expecting large change of sea surface height in the simulation. However, you can see that over the 100 years, the sea surface height in this simulation decreased about 8 meters. So this is a very large value. In the water budget terms, you can see on the left, there are evaporation, sea ice, fresh water, river runoff, ice runoff, rain, snow, and fragile. So those budget terms exist in different model components. For example, evaporation, rain, snow, those are in the atmosphere component. So we are wondering how large is the error caused by the atmosphere model. Is it positive or negative? Next slide. So here I show a figure from the IPCC AR5 report. So this shows the sea level rise from 19th century to year 2000. So the observed sea level rise in the this 100 years is about 30 centimeters. So this is caused by changes in the external forcing like greenhouse gases. So however, with a relative total water conservation error of about 0.3% per year, the model will simulate the same amount of sea level rise in the central line simulation. So as we observed here, so this means that the smaller errors are not always trivial. Next slide. However, small errors often come along with model development. So new features, capabilities bring new challenges in model development. So they might be incompatible with other components. Fixing one problem might cause a further problem. Sometimes these errors are not obvious. As an example here, I show this Samsung Galaxy Note 7 cell phone is a very nice phone, but very little problem cause a big threat to the people life. So in our model, we try to avoid not only the big error, but also the small accumulative errors. Next page. So here I show the result from an earlier version of E3SM capital model. So the simulated water conservation error can be converted to an implied sea level rise due to water conservation error caused by the atmosphere model in the 100 years. So this value is about 14.5 centimeter. So compared with observed sea level rise in the past 100 years, so this is almost half of the magnitudes. So this error is pretty large. Next page. So we try to identify and quantify the water conservation error from different sources in the atmosphere model. So we define error given a certain period, t-1 to the current time step. The error is defined by the modeled error minus the expected modeled water column burden minus the expected water column burden. And this can be, the expected water column burden can be calculated using the previous time step water content burden and the precipitant flux and surface moisture flux. Next slide. So we did a comparison between CAM 5.3 and the E3SM atmosphere model. So on the left, I show the relative water conservation error in the 5-day simulation. The x-axis is the days, y-axis is the relative conservation error. You can see here that the EAM model with an alpha has a pretty large relative conservation error. For NE30 is about 0.1%. For NE120 is about 0.3%. So both of them at the equivalent at the same magnitude or even higher than the error equivalent to the 20th century sea level rise change due to anthropogenic forcing. So this may cause a big problem in our couple simulation. However, when you look at the CAM 5.3 model, the error is very small. If we magnify the lower part of the figure on the left, we can on the right we show the zoom in figure. We can see that the CAM 5.3 model at 2 degree, the relative error is at around 0.002%. It's very small. After we fix now the error in the atmosphere model, we can get a even smaller conservation error compared to the CAM 5 FV model. So next slide. Here I show the schematic plot of the CAM 5.3 model and the EAM V1 alpha model. So we can see what has been changed in those in our model compared to CAM 5.3. So first we can see that the dicore has been changed from finite volume dicore to the spectral element dicore. And this also involves the physics dynamics coupling change in the model. Also, we notice that the 30-line model has been changed to the L72 level. And there are some physical parameterization changes in the model as well. For example, the UW, turbulence, and macrophysics parameterization has been changed to club. MG1 has been changed to MG2. And there, in the new model, there are subcycling between club and MG2 coupled with a coupling time of 5 minutes. And we also see that the vertical diffusion calculation in CAM 5 previously is very close to the QNAC4 fixer. However, in the new model, the QNAC4 fixer is far away from the club turbulence scheme showing on the left, showing on the right. So this might cause a coupling error in the model simulation. Next slide. So we identified the problem. Should be E3SM entity model. So on this slide, the red color indicates the large and corrected value, corrected terms in the E3SM V1 beta onwards. And green color indicates small but not corrected errors. For example, the internal error in the conservation error in the physical parameterizations like deep convection, club, and MG2. And the blue color indicates some error terms to be corrected in the future versions. So let's focus on the physical dynamics coupling errors. So on the top, the red color shows there is a physical dynamic coupling method change from a parameter change from 0 to 2 by by making these changes, we can reduce the physical dynamic coupling error to machine runoff levels. And we also see that the blue colors, one is related to the QNAC4 fixer. We change the fixer to a mass conservative fixer in the model, and we also have another water conservation fixer for the QNAC3, so that we can conserve the water by not clipping the negative water tracers. So next page, we quantify the error in the M3 model. So there are 5 error sources in physical dynamic coupling, or the at the interface of between club and the EAM model, QNAC4, QNAC3, and internal errors in the physical parameterizations. And we did experiment using different kind of configuration of the model. Panel A shows the default V0 model. In the model, we use UW shallow convection scheme and macrophysical scheme, MG1 macrophysics, and L30 levels. Panel B is a scientific experiment by only changing the vertical levels. Panel C is simulation with club and MG2. Panel D is a V1 alpha Anfield model. We can see that in the in all of the panels, there is a large physical dynamical coupling errors. This error is the dominant errors in all those simulations. And when we change the vertical resolution from 30 level to L72 levels, we notice that the QNAC4 errors started to appear. This is because now the surface layer in the lowest model layer is very small, about 20 meters. And using the same model time set of about 30 minutes, there is some coupling error associated with the QNAC4 errors. Panel C shows impact of club and MG2. We see that there is error caused by approximation of latent heat flux in the at the interface. This error is relatively large compared to errors, but smaller than the physical dynamics coupling errors. And altogether, so this V1 alpha M3 model has a pretty significant water conservation errors. Next page. Here I show the diagrams of the physics dynamic coupling is a EAM model. So red panel shows a V1 alpha default. You can see that the atmosphere physics tendency is applied 2 times in the dynamical core. And after the first physical tendency application, there is clipping, and then the dicore calculation. And after the first dicore cycle, there is another tendency application for the physics. And then after that, there is clipping as well. At the second time, when the physical tendency is applied, all the physics tendency is not consistent with the new state. And so the negative tracer can appear here. And if they are clipped, this will cause very large conservation errors. However, if you look at panel A, which is used in the default FV, CAM5 FV model, and also in a certain configuration of the SE dicore, on the left panel, the Anfield physics tendency is applied at the beginning of the physical dicore calculation. And in this way, there is no physical dynamic coupling errors in water conservation. So we managed to apply new physical dynamics coupling methods. It's a hybrid coupling method for dynamical variables and water substance variables. I'm not going to tell the details here, but you can see in our paper later. Next slide. Here I show the sensitivity to the temporal and spatial resolution in the model. So left panel shows the time step sensitivity. Here I use the N11 model to do the sensitivity simulations. X-axis is a time step in second in log scale. Y-axis is the equivalent high changes in the 100-year simulation, also in log scale. So by looking at this plot, we hope to see the convergence from using larger time step to using small time step, or fine coarse resolution, or to the fine resolution. So for the time step sensitivity, if we increase time step, so we will have large coupling and splitting errors. So this is true when you see the figure that when we have larger time steps, the error is larger. On the left, when we look at the resolution sensitivity, here I show the I do the older simulation, N11 to N30, with the same time step of half an hour. So when the resolution is increased, we will have stronger tendency and larger gradient of especially for the hydrometers, color hydrometers. So we also expect the error to be larger at higher resolution if the time step is fixed. Next slide. So after fixing the physical dynamics coupling error and the errors associated with liquid latent heat flux calculation at the carbon interface, we have been able to reduce the error greatly in V1 beta. So the error is reduced by a factor of 80 for the N30 simulations. However, if you look at the panel A, for the N11 model, so the error is still very large. That is because in this model, the time step is very large, 2 hours. So the coupling errors in QNAC4 can cause large water conservation errors still in V1 beta. So this must be remembered when we do some sensitivity simulations using the lower resolution model. However, for the NE16 onwards, NE16, 30, 120, all those simulations have very, very small errors in the model. So at least for those resolutions, we are safe to use coupled simulation in this version. Next slide, we can further reduce the error in the model by removing the QNAC3, QNAC4 errors using the new fixers, mass conservative fixers. We can see that for every resolution from NE11 to NE120, the simulated water conservation error in the Amsterdam model is very small. This error is caused by the remaining error is caused by the internal error in the physical parameterizations, which is very difficult to remove now if we are not going to change the structure of the parameterization greatly. And there are also some machine roundout errors associated because when we do the water conservation error calculation, we have to use hydrometer values at a very different magnitude. Next slide. So let's look at the water conservation error in the new coupling model again. So compared to the here on the in the figure, I show the relative water conservation error in the 100-year simulation compared to the E3SM alpha version. The E3SM beta coupling model has a very good water conservation. So if so, the relative error is reduced by a factor of 80. So the implied sea level rise due to the remaining water conservation error in the 100-year simulation is about 2 millimeters. So it's very small. As I said, there are some remaining conservation errors, Q-3, Q-4, and internal errors, and this can be fixed in the future versions. So to summarize, next page. To summarize, we found that conservation error existed in the E3SM alpha version, and the numerical choices in the physics dynamics coupling and model physics have very large impact on the conservation errors in the MC model. So the Amphier V1 model converts water much better than before, but it still can be further improved from 2 millimeters per century to negligible water conservation error. To reduce the process coupling errors is very important, and this calls for smaller time steps, better coupling, or better numerical treatment in the model. And last but not least, consistent treatment of the water and energy conservation in each parameterization is the last step for perfect conservation in the model. So if you are interested in the details, please look at our paper that has been submitted to GMD. Then what's next? Next page. So we are going to maintain good conservation properties in highly complex physical parameterizations and the coupling between them in the E3SM atmosphere model. So we focus on 3 components or parameterizations. The club part is handled by the static convergence project. The MEM part, the coupling between aerosol emission, dry deposition, and vertical diffusion can be better handled if we solve them together using some implicit solvers. And the P3 cloud microphysics under development in the for the E3SM atmosphere model, we are also trying to make the water and energy conservation not only conserved but also consistent in the model. So this is work for in the CNBV MCS project. And the other one topic is that the energy conservation and consistency between water and energy conservation across different model components have to be considered in future model development. So that's all what I have. Thanks very much.
We have time for a few questions if there are any. I think just speak up, that is, Renata, put on there, speak loudly because we're recording the presentation.
This is Dorothy. Oh, go ahead. Go ahead, Zhang.
So, I just want to ask the impact of the recently found bug in the land model energy conservation has anything to do with this problem?
I think I cannot answer that question. So if there is error in the individual model components, this will cause conservation error in the end in the couple simulation. So the first figure I show in the presentation here is it's from a very old model version. We know that there's a large problem in some model components, and such error is not existing in the current V1 coupled model. This is for sure.
Okay, thanks. Let's talk about this later.
So this is Dorothy. I have a question about, and I don't know whether Peter Caldwell is on, but I know he's been working on separating dynamics in physics, which I guess might amount to taking larger time steps. I don't know, something like that. I'm wondering if that's going to create a problem. Or maybe this is just a convective issue that's different than what Peter's working on. Do you happen to know?
Peter's postdoc, or not a postdoc anymore, a scientist, Anna Danaher from Livermore Lab. I had a discussion with him before. He told me that he had encountered similar issues when he did the physics dynamic separation work in the past, but I'm not sure whether he already solved the problem or not. But I think similar problem exists also in his work.
All right, thank you. Something to follow up on, I guess.
Yeah.
Okay, any other questions? If not, Renata, can you give the screen to, got him?